Cambridge is a very exciting place to work. The computer laboratory has been involved in a lot of historic work in computer science. Not very far from here, not only was the electron discovered and the atom first split, but also the invention of some of the key concepts in computer science, the development of software libraries, of microprogramming, many other things. At St. John's here, Maurice Wilkes, who invented the software library, was also involved in the development of ideas in capability systems and hardware and software protection. At the computer laboratory, we have experts that span the field. Our recent contributions include systems like VNC and Zen, and also our own capsicum work. They span natural languages, computer architecture, programming languages, operating systems, and security. Working on a project called Cherry, which is looking at the hardware-software interface in order to understand how to improve computer security.
My name is Robert Watson. I am a computer scientist at the University of Cambridge. I'm a FreeBSD developer, and I'm also a member of ACM.
When we were doing our work on Capsicum, which is a computer operating system security framework, we discovered that we really wanted to study the structure of applications and application security rather than operating system security. In doing that, I think we were very successful, but we also found that we were constantly encountering the limits of current hardware design. That as we wanted to create more and more sandboxes to support elements of the application, we ran into performance problems, we ran into programmability problems. And to solve these problems, we really had to turn back to the instruction set architecture and ask, are there ways that we can improve it? It's interesting. When we worked on Capsicum, we found that there was a large open source operating system corpus, open source application corpus that allowed us to ask very complex experimental questions about real-world software. We can analyze it, we can modify it, and the results are realistic and interesting outside of the space of research. But when we turned to hardware, we found that researchers were working with very small models of current systems. I don't want to say that they're toys, but they were intended as experiments to study very specific problems. They usually use very small software applications, handcrafted micro benchmarks or other industry standard benchmarks, but not complete software systems. The problems we want to study require us to work with large-scale real-world operating systems and applications, web browsers and office suites. And so we really felt there was a gap. The first step in our research was to fill that gap. So the interest really comes out of our work in Capsicum on discovering that it was the limits of the hardware that prevented us from efficiently expressing some of our goals. For example, we were interested in subdividing large-scale applications, web browsers and office suites, into many different parts, each running in their own sandbox. If you look at current applications, such as the Chrome web browser, they try to do this. They assign particular tabs to particular processes. Initially, they did this for reasons of robustness, and then you make the observation that if you're running them in separate processes, you could also run them in different sandboxes, which is it's pretty exciting that we're starting to deploy sandboxing technology in that way. And yet, as you scale up the number of tabs, there's an executive decision in Chrome. It says as you go above, maybe 30 or 60 sandboxes, we're going to start conflating them, pushing tabs into the same sandboxes because we can't create more processes than that. The system just runs out of oomph. So as a direct consequence of a low-level aspect of hardware design to do with how we create processes and how we represent protection, we see an effect on the security of the system directly at a user-visible level. With a web browser, we would really love to be able to process every individual image in its own sandbox. Right? The consequences of a particular image containing an exploit will be limited to just the processing of that image. And this is important. It makes sense to put different tabs in different sandboxes because they often represent different security interests. But as we deploy cloud applications such as webmail, so if you look at Gmail, the idea that a tab represents one security interest becomes ludicrous. You're receiving emails from many different individuals, you're dealing with different accounts and mailboxes, you have attachments being forwarded to you by your friends. There is no one security interest there. It's not just Google. It's many different parties. And so we'd like to be able to create sandboxes to represent all those different interests in order to limit their influence. If you send me an attachment that contains a bad image, it should run in a sandbox that has no access to any of my other messages or any of my other mailboxes. And as we try to scale up software to use these features, there are visible performance degradations. You go from web pages popping up instantaneously to images popping up one at a time on the screen. It feels very 1980s watching them appear, 1990s watching them appear as the web page loads. And that kind of visible performance degradation is unacceptable to companies producing products that have the smooth user experience that we have today. So we need to push back on the hardware design and say we need to now optimize something very different. The current trade-offs between protection and virtualization developed in the 1980s and 1990s, and they were focused on a world in which, a world that was full of many fewer adversaries. Today we're used to the idea that we receive a constant stream of malware, of programs designed with malicious intent. In the 1990s, this was clearly not part of the design framing, and so a reasonable set of optimizations for that world were made, a set of design trade-offs that addressed the problem that was present then, focused primarily on software robustness. Today we have this desire to have many, many different compartments, which was not the design optimization in that system. So we want to shift the design trade-off there with minimal disruption to software. On the whole, in the world of protection, this is something we can do. Protection has historically been the domain of the operating system, of low-level system libraries and so on. So we think we can do this relatively non-disruptively, which I think is in part an outcome and an insight that came out of our Capsicum work, this goal to produce hybrid capability systems. When we started the project, we ran into an immediate problem, which was that we needed to build a team of people able to build a research platform in the hardware-software interface. This means experts in computer architecture, operating systems, programming languages, applications, and program analysis. We have all of those people at the computer laboratory, but they don't always collaborate, and they certainly don't collaborate on large team projects of the sort that we had in mind. And this is a result of, I think, siloization in the field, that if you look at our publication venues for research, if you look at the way that we train our computer scientists and computer engineers, they're forced into narrow tracks. The only way to gain enough expertise in any specific subdiscipline is to focus on that almost to the exclusion of all else. And this has a huge impact on the kind of research that we can do. It means that any one individual or even a small research team has trouble finding the breadth to answer questions such as, what happens if we change the structure of the hardware-software interface? What happens if we make protection more efficient or less efficient? What are the implications for the entire software stack? You need a high level of expertise to build systems like this. You have to be able to build a processor, build an operating system, change fundamental aspects of system software, which is one of the most difficult aspects of computer science. I think software engineers have little experience with hardware, in part because of the siloization problem, that our researchers tend to work in narrow fields, they train students in equally narrow fields, and that the interactions between these require collaborations of the form that we don't often perform. And yet, some of the most exciting successes in computer science and in research as a whole, some of the most exciting developments in computer science come out of this hybridization of different fields, collaborations between people with different interests and different backgrounds. And this is reflected in how we teach our students. Interesting. I think people think of instruction set architectures and the hardware-software interface as being very static. As programmers, we're used to programming to a fixed set of hardware constraints, targeting instruction set architectures designed 20 or 30 years ago in large part to allow software to continue to run. And we benefit from that hugely. However, I think it's also a false impression. At the same time that industry seems to have settled on Windows and Wintel for workstations and servers, There's enormous change going on under the hood. The widespread deployment of graphical processing units, or GPUs, is a fundamental change in the hardware-software interface. Likewise, extensions to support virtualization, offloaded networking. These are all changes to the hardware-software interface that influence how software developers work. We try to hide that from them because we don't want to have to chase every individual small change, but we really see enormous change in industry. Another example is the widespread adoption of RISC processors. It's interesting, a few years ago we were talking to a research sponsor and we said, we'd like to build this platform and we'd like to start with a RISC system. This makes it easiest for us to do our research. And they said, but isn't RISC dead? Didn't RISC lose? Everyone uses Intel. Well, this is obviously not true. If we look at the deployment of mobile phone systems and tablets, all of those systems come out of ideas that were developed during the 1980s and 1990s in RISC. Quietly and under the hood, the majority of consumer devices have changed from running Intel CPUs to running ARM CPUs with a very different instruction set architecture. Yet, from the software development perspective and the user perspective, that experience has been relatively seamless. So there is the opportunity to change the hardware-software interface to improve power, behavior, energy efficiency, security, performance, and other aspects without disrupting the adoption of technology. And yet, we still find that software developers work siloed. They tend to consider the hardware as a fixed point in their research. The variables are all in software. One of the challenges for us is to be able to perform what we call multivariable research. We want to be able to change both the hardware and the software in order to explore whether we're simply finding local maxima for performance or energy efficiency by not fully exploring the design space. One of the aspects of the work we've been doing is to explore hybrid systems, systems that both contain many of the properties of conventional designs, but also critical modifications that affect some portion of system design. In Capsicum, we introduced new operating system primitives that allow us to incrementally deploy a new security model. We can look at one library, we can look at a key application, but we don't have to deploy the changes to all aspects of the software. This is neither incompatible with our desire for radical change in software and hardware interfaces, nor extremely disruptive for software developers. It is possible to do both, and we see that possibility in this widespread adoption of GPUs and virtualization as well. I think there are enormous tensions in the art of hardware offload. What we're doing is we're taking functionality that exists in software, we're now encoding it in a form where it's written by a different person, it's implemented using a different technology, and it executes in a different place. The reasons for hardware offload have changed a lot. Originally, we introduced hardware offload in order to provide greater parallelism. In the 1990s, with the migration to 100 megabit Ethernet and later to gigabit Ethernet, the act of moving checksum processing from the general purpose CPU to the card exploited parallelism. CPU cycles were freed up to do real work, the actual work of the application programmer. Now, we still perform checksum offloading, but we do it for a different reason. We do it because of the speed of light. The only place where all the information we need is neatly in one place at one time is at the point where the information is being sent out of the NIC itself. The contemporary processor has lots of CPU cycles. It's able to perform checksum calculations very efficiently. And even if it couldn't, we could modify the instruction set architecture to do that, like we've done with cryptography. But instead, we choose to place it in the NIC where the right thing happens at the right point in time. And we see this throughout work on offloading. The desire to shift GPU processing back onto the main processor comes out of the fact that there's a tight coupling between the data processed by the application and for the purposes of graphics. And so the same question comes up in our work in hardware offload, the same tensions. One of the downsides to hardware offload is that we have this transition of ownership of maintenance for an aspect of the design of the system. In TCP offload, this causes enormous problems. We actually end up with two different network stacks. The network stack maintained by the general purpose operating system programmer and the network stack maintained by the NIC vendor. And one of the reasons we've seen a lot of resistance to full TCP offload is that you end up with interoperability problems and surprising interactions. You end up with the inability of the OS vendor to provide in-field updates to aspects of the network stack. We want to avoid that problem in the work that we're doing. We want to provide new tools to the software developer and yet leave the software developer with as much control as possible. I think you have to look at this from a raw computation perspective. There are lots of reasons to shift the hardware-software interface, but one of the most motivating ones for industry is performance. In the Cherry work, we're interested in a specific performance problem, that as we increase the number of compartments in the system, performance goes down extremely measurably. The cost of switching between protection domains is noticeable. Current hardware has been optimized for what we think of as hierarchical security models, ones that are intended to support a series of asymmetric trust relationships. The application fully trusts the operating system. The operating system fully trusts the hypervisor. And we have very efficient context switches between those domains. What we don't have is extremely efficient context switches across mutual distrust. When two different sandboxes are communicating with each other in a tightly coupled way, yet they mutually distrust each other, we experience enormous cost switching to the operating system, copying data back and forward. Even with the help of the virtual memory system, we discover enormous bottlenecks. Zero copy message passing doesn't solve the problem of efficient switching because it actually exploits hardware mechanisms that are themselves inefficient in the presence of switches between different protection domains. Just as a simple example, the translation look-aside buffer in the memory management unit is an associative lookup. This is something that's very inefficient to do in hardware. It's a component that runs extremely hot and uses a lot of power. When we have multiple protection domains, multiple entries appear for the same piece of memory in the TLB. And as we expand the number of protection domains exponentially, which is something that we'd like to do to support the application programmer, use of the TLB becomes less and less efficient. You might reasonably ask, why is it that we need new operating system security at all? After 30 years of research and development, of shipping thousands, hundreds of thousands of products, what was missing that required us to add new primitives to the operating system? The answer is really quite interesting. It's a migration from the focus of security being in the operating system to the application itself. Previously, operating system security primitives were focused on the relationships between users in a multi-user computer system. Today, it's not so much that every computer has many users, so much as that every user has many computers. In my pocket, I have a small Unix machine in the form of a phone, I have a tablet, I have a notebook computer I carry around with me. The focus of security isn't about my sharing those machines with other users. The focus of security is on helping applications frame the relationships between me and all the other users I talk to over the internet. If we look at a web browser, which is an example of what we think of as a monolithic application, this is an application that interacts with many different parties, none of them other users on the same computer as me. I use it to visit my banking website, I use it to reach my email, I use it to read the news. In every case, they're shipping applications to me that run on my own computer. This is not something that conventional operating system security was designed to address. And so in Capsicum, we wanted to introduce new primitives that allowed application programmers to express their own security properties in a very extensible way, that allow sandboxes to create further sandboxes. A sandbox that might process a tab, in turn creates a sandbox for every site that we visit, which in turn creates a sandbox for every image that is processed. This is a very different perspective. And that transformation that we see in Capsicum is also something that we're now looking at in Cherry. Conventional hardware design for protection is designed to support the operating system developer, to allow this asymmetric trust relationship. But what we want is computer hardware that can support application developers who deal with many different security domains. We want not to have to turn to the operating system for all these features, but the hardware, because we need it to be very efficient. We need these changes to happen extremely frequently. I think one of the most valuable resources we have as operating system researchers is the open source software corpus. Not just open source operating systems, but also an enormous suite of realistic and widely used and production-ready applications. Many of these open source components were originally developed in academia by researchers in order to support research, but they've become valuable tools that are used throughout industry. One of the benefits of having this large open source software corpus is the ability to do reproducible experiments. I work with real software. I make the modifications to that software in order to test a hypothesis, and you can reproduce my results. Not only that, you can perform your own experiments, changing different aspects of the same software. So we're able to have a very productive research relationship in which we build on each other's own results. Another benefit to the open source software corpus is the ability to collaborate, that we can share research results with each other, use them to build common platforms. This is something that is missing in the hardware community. They're not able to build on the same platforms, they're not able to compare their results nearly as usefully. And this is something that has to change if we want to do effective hardware-software research.